Hello everyone, I'm Suhas and I'll be presenting our work on learning generalizable perceptual representations for data efficient no reference image quality assessment. Image quality assessment has been a long-standing area of research and has witnessed numerous developments over the years. Objective quality assessment refers to the prediction of picture quality that correlates well with human opinions or perception. In particular, we are interested in a subtopic of quality assessment, namely the no reference image quality assessment setting. Here, the quality of an input image is predicted without the use of a corresponding pristine reference image. In this line of work, several NR-IQA methods have been developed, but they come with certain limitations. Most NR-IQA models often require a large amount of annotated data, and obtaining these annotations through large-scale human subjective studies is often cumbersome. Moreover, these methods are neither generalizable nor are they data efficient. Over the last decade, several types of NR-IQA algorithms have been developed. The most common type is the supervised class of algorithms, where deep models are trained with the supervision of mean opinion scores or MOS. However, these methods are often burdened with the requirement of large amount of training data and also generalize poorly. Here are some examples of supervised methods. In order to improve generalization, self-supervised models have shown a lot of promise in constructing very good feature representations, particularly through contrastive learning. However, the training strategy often involves a fixed set of distortions, leading to poor generalization to unseen distortion types. Here are some examples of contrastive learning based methods. While self-supervision offers good image quality representations, recent developments in vision language models have shown to benefit NR-IQA through their inherent generalization capabilities. For instance, vision language models such as CLIP are used to predict image quality through the alignment of image and text representations. However, a lack of task-specific fine-tuning limits the generalizability of such models. Here are some examples of CLIP being used for NR-IQA. In order to learn better generalizable representations and have data efficiency, the data efficient NR-IQA problem comes to light. Here, an NR-IQA model is fine-tuned using limited samples on an IQA dataset. However, some methods still require either end-to-end fine-tuning of the model or require additional parameters to be trained. Although prior work exists in the data efficient setting, there is still scope for learning more richer and informative quality representations. In our quest towards a holistic approach for data efficient NR-IQA, we propose to learn generalizable representations for quality that can be trained on a target dataset using limited samples. We learn two sets of representations, one through a low-level model that learns distortion-based quality information, and another through a high-level model that learns the scene context. The two sets of features are then fused, and we train a simple support vector regression using limited samples. To begin with, we present an overview of the low-level model. Typically in contrastive learning, we have an anchor representation and a positive that we try to bring towards the anchor, and we have multiple negatives that are pushed apart. In the context of IQA, contrastive learning is done in a content conditional manner where the positives are chosen to be quality preserving augmentations and the negatives are different distorted versions of the image. However, there is a problem with this formulation in the sense that different distorted versions of an image could be of same quality. To this end, we propose a quality-aware contrastive learning approach that makes use of a perceptual similarity measure between distorted versions of an image. The role of the similarity measure is to assign a soft weighting between a pair of images. In other words, two images are considered positives with a factor of S. This manifests as a weight factor in the contrastive loss, ultimately allowing us to learn distortion type agnostic representations. In order to generate the positive augmentations while training, we employ the popular spatial fragmentation technique. Here, each image is divided into grids, and from each grid location, one mini patch is randomly sampled. The idea is that quality across mini patches in a local region remains fairly constant. Now, we present details about the high-level model. We leverage the generalization capability of the recently developed and successful vision language models, specifically the CLIP model. Our approach involves an unsupervised contrastive learning over groups of images that correspond to high and low quality. In order to compute quality pseudo-labels for contrastive learning, we use the difference in alignment of image representations with that of two antonym text prompts that are relevant to quality, such as good photo and bad photo. For a batch of images, the quality pseudo-labels are computed according to this expression and are arranged in increasing order. Next, two groups are selected from either ends of the list, and the image encoder is trained using the contrastive loss over these groups. The representations within a group are brought closer, and the representations across groups are pushed apart. This enables the learning of context-based quality representations. Now that we have learned the two sets of representations, we evaluate the performance on two popular user-generated IQA datasets, CLive and Conic 10K. We observe that our approach consistently performs better than existing NR-IQA methods in the limited data setting, even outperforming end-to-end fine-tuned models. In addition, we also provide a zero-shot quality prediction framework where no fine-tuning is required on a target dataset. To predict low-level quality, the statistical deviation of the image features is computed from a set of pristine images. And to predict the high-level quality, the difference in similarity of the image representations to two antonym text prompts is computed. We observe that our method outperforms other zero-shot methods, even including the CLIP-IQA method. Here, we show the complementarity of the high and low-level features. For instance, if we take a look at the image on the top right, which is an out-of-focus blurred image, the high-level model is able to make a more accurate prediction of quality because it is rich in contextual information. And if we take a look at the bottom left image, the high-level model is unable to make an accurate prediction because of low contextual information in the image. To conclude, we presented a two-stream representation learning method for data-efficient NR-IQA. We presented a low-level model that learns representations agnostic to distortion types using an unsupervised quality-aware contrastive loss. We also learn contextual information through the high-level model using an unsupervised group contrastive learning strategy. Our framework offers the advantage of not requiring end-to-end fine-tuning and shows good generalization while trained on limited samples using a simple linear SVR. In case one does not have the luxury of training with labeled examples, we also offer a zero-shot prediction method as well. Thank you.